As you can see from the title of this video, this tutorial is about learning how to depict polyatomic ions within compounds. To this point, we've learned how to draw Lewis structures of a lot of different things. Lewis structures of elements, Lewis structures of ionic compounds, Lewis structures of covalent compounds, Lewis structures of polyions alone, and now we need to look at how do we tackle a polyion when it's part of a bigger compound. Well, the first thing you have to realize about polyatomic ion compounds is that they are exclusively ionic bonds. The polyion may be covalently bonded, but you have to realize that when a polyion forms with a nonmetal or a metal, that it's going to lead to an ionic bond, a transfer of electrons. That being said, you will be able to identify a polyion in a compound, right, by recognizing that you'll have one of two things. You will either have a metal plus a polyion, or NH4 plus a nonmetal. The reason there's two scenarios and that exclusively you see NH4 appear is because NH4, ammonium, is one of the only positively charged polyatomic ions that there is, and we really focus in on that and not many of the others. Other than that, all of the polyions that we learn are negatively charged. So you'll have to put those with a metal, leading you to a metal with a polyion or NH4 with a nonmetal. Because these are going to be ionically bonded, you have to realize what type of picture you're going to draw, and because it's ionically bonded, that means you are going to depict a before and after scenario. Once you realize that it's a polyion in a bond, it is not terribly different than doing an ionic structure. The only difference is instead of just looking at the periodic table and pulling the dots off of an element by looking at the group, you have to draw your polyion and see where the electron needs to come from. So let's take a look at an example. KBrO3, known as potassium bromate. Whenever I'm looking at this to try to figure out the type of bonding, the easiest way to know there's a polyion is by doing this. If we look at K with Br, that would be a metal from the left of the staircase with a nonmetal from the right. That tells me ionic. If I look at Br with O, Br's to the right, O's to the right, that's nonmetal, nonmetal, that tells me covalent. Whenever you have competing ideas, right, one thing telling you it's ionic, one thing telling you it's covalent, that is what indicates you've got a polyatomic ion compound. Right? Otherwise, it would just be something like this, BrO3, which would be covalent, or KBr, which would be ionic. So the only time you get metal, nonmetal, and nonmetal, nonmetal is if a polyion is present. If that happens, we need to do a before and after picture. So let's do that. Right? The first thing you're going to do is figure out where is the polyion. And the polyion will always be the non-metal part or the NH4 part, the nonmetal with hydrogen. So you separate those two things. So I'm going to have potassium, and given its location on the table, potassium in group 1 gives me 1 dot. Now I'm going to keep the polyion together. Right? BrO3, bromate, right? I'm going to have to draw it. So if we take a look at this, we're going to put Br in the center and surround it with oxygen. Just like any other covalent compound, I'm going to have to add up my valence electrons, right, and get my electron bank. Right? Br gives me 7, and O gives me 6. So 7 plus 3 times 6 means I have a grand total of 25 valence electrons to work with. Then I draw my single bonds. 3 single bonds will burn up 6 of those, leaving me 19 electrons to try to fill the octets of all of the atoms there. So if we start on the bottom, oxygen needs 8, it only has 2, so we'll give it 6. Same thing here, so that gets us 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I still have 1 left, and if there's extra, it goes onto the center atom, 19. So if you take a look here, you're going to see that when we check our octets, that oxygen, oxygen, and oxygen are all happy with 8, but bromine, 2, 4, 6, 7 is unhappy. We also have run into a scenario that we can't cure it by creating double and triple bonds, because if I were to push 2 of these into here, I would then give bromine 2, 4, 6, 8, 9, which is just as bad as having 7. It still doesn't fill the octet rule. So you've run into a scenario where bromine wants to gain an electron and potassium wants to lose an electron. And that is exactly what happens. We see a transfer of the electron from potassium over to bromine. So then if we go and draw ourselves an after picture, I still have potassium. It has no dots left because it gave the electron away. And because it gave 1 electron away, it's a +1 charge. And now I have my polyion that will look identical to this, except it will have 1 extra electron. So we'll have the 2 dots here, single bonds, and then our 6 dots on all of these. And because it gained 1 electron, it gets a -1 charge. So before, when we were learning how to draw polyions, what you were really learning how to do is draw what the polyion looks like in the after picture. And that is why they always went in brackets with their charge outside, because there was no way that you could draw that picture correctly if you did not have the extra electron. Like, we were randomly just saying, oh, BrO3 -1, and we pulled the electron from the -1, but in reality, it will always come from something else. So let's take a look at another. Something like Na2CO3. Right? Sodium carbonate. Again, if I tried to attack this like we normally do, the first thing we would want to figure out is it ionic or covalent? So if I look at Na, that is to the left of the staircase, it's a metal. With C, that's to the right of the staircase, non-metal, that tells me ionic. If I look at C with O, I have a non-metal plus a non-metal, that tells me covalent. That's how I know there's a polyion in here. So the polyion's always the non-metal part, so it's the CO3. And then we're going to have to do a before and after picture to accurately depict this. So if you look at the formula, we have 2 NAs, and because sodium is in group 1, they each have 1 dot. Then I have to try to draw the structure for CO3. Right? C is here. Right? O is here. C needs more to get to 8, so it goes in the middle. Draw your 3 O's. Figure out how many valence electrons you're working with. Carbon gives you 4. Oxygen gives you 6. So 4 plus 18 gets us 22 electrons to work with. Make your single bonds. 3 single bonds burns up 6, leaving us 16 electrons. So now we'll try to fill our octets from the outside at 1, 2, 3, 4, 5, 6. That's good. 7, 8, 9, 10, 11, 12. That's good. 13, 14, 15, 16. Right? So what's happened is I have filled the octet of this O and this O, but carbon only has 6 and oxygen only has 6. So if you try to solve this problem, you may first try to create a double bond somewhere to make these happy. Right? Well, if you take 2 off of here and push them in here, you've made carbon happy, but oxygen is still unhappy. Right? It has 2, 4, 6, 8, but 2, 4, 6. So that doesn't seem to do the trick. We could do the same thing here, move 2 and push them in, right? Making carbon happy, but this O is still unhappy. And no matter where you make a double bond from, there is no way that you can make the oxygen here on the outside happy with the number of electrons that we have. Now, your double bond could fall any of these places, here, here, or here, which is an idea we'll talk about later called resonance. Right? But you will run into the scenario where I need 2 electrons to this oxygen to make oxygen happy. And sure enough, sodium in each case wants to lose 1. So each sodium will lose 1 to the oxygen, and that will allow it to get the 8 that it needs. So in the after picture, I will have 2 NAs. Because they each lost 1 electron, they both get a +1 charge. And then I'll have a polyion, which always goes in brackets. C in the middle. We made our double bond here. Single bond. Single bond. And now we have the 2 electrons from sodium in here. And because they gained 2 electrons, this would get a -2 charge. Everything else remains the same in terms of principles of things. Remember, we usually want our charge to add up to 0. +1 + 1 -2 is 0. And in the covalent polyion, you have met the octet rule, or duet rule, so to speak, in any of the other ones that we would try. So that is what it looks like when you have a polyion within a compound. You mix what we do with covalent with the ionic, but in the end of the day, it ends up being more ionic because you have to draw a before and after picture. If you're still having some trouble, please feel free to come in. Otherwise, I hope this cleared up any of the problems that you may have been having.